Okay, our discussion is on deflection of beams. So for this, in this chapter, we consider the deflection of statically determinate beams. So meaning to say statically determinate beams. So that means that you're going to analyze the beam using the equations of equilibrium. So because the design of beam is frequently governed by rigidity rather than strength, the computation of deflection is an integral component of the beam analysis. So basically for this, we have to take note that in the design of beam, it is governed by rigidity rather than strength. So what's the difference between rigidity and strength? So when we talk about strength, that is the power to resist force. So meaning to say there is an applied force, and if the material can resist that power or that force that is being applied, so it has the capacity to resist the force that is being applied. So we're talking about the strength. So when we talk about rigidity, so it is defined as the property exhibited by the solid to change in its shape. So that is when an external force is applied to the solid material, there won't be any change in the shape. So basically, if there is an applied force on that particular material, so there will be somehow, the solid material won't go any further change in its shape. So that is talking about rigidity. So for example, building codes specify limit on deflections as well as stresses. So for the deflection of beams in the analysis for statically determinate beams, so it is the deflection, the computation for deflection is very important. It plays an integral component on the beam analysis. So for example, building codes specify limits on deflection as well as stresses. So excessive deflection of a beam not only is visually disturbing but also may cause damage to other parts of the building. So if there will be a deflection on on a certain material, or for example, if we're talking the material that we're talking about is all about beam, so if there will be an excessive deflection on the beam, if there is an excessive deflection that may occur in the beam, it is not only a disturbance in terms of visual, but it also cause damage on other parts of the building. So meaning to say, if there will be a certain deflection on one component of a certain structure, and that one component is we're referring to the beam, so basically it will cause disturbance not only on the visual side, but it will cause damage on other parts of the building. So that is the main reason why the building code limit the maximum deflection of a beam to 1/360th of its span. So meaning to say, there is a limitation, there is a specified maximum deflection based on the building code. So that is equivalent to 1/360th of its span. So deflection can also govern design of machinery. For example, the cars and aircraft. So in that design, for example, the deflection must be kept below the dimensional tolerance of the parts being machined. So for car and aircraft, it must have sufficient rigidity to control structural vibration. So that basically how deflection is being applied in the design for machinery, specifically for cars and aircraft. So we have to take note that deflection also play a crucial role in the analysis of statically indeterminate beams. So meaning to say, deflection concept is very important also. It takes a vital role in analyzing statically indeterminate beams. Of course, we know that statically indeterminate beams, meaning to say we cannot make use of the equations of equilibrium to analyze the beam. So since there is a limitation for statically indeterminate beams in the use of equations of equilibrium, so we make use of the concept of deflection. They form the basis for compatibility equation that are needed to supplement the equations of equilibrium, as we discovered in our analysis of actually loaded bars and torsion of shafts. So basically, in our previous discussion, we have identified the use of deflection concept in deformation of compatibility equations that is necessary to supplement the equations of equilibrium, since we cannot make use equations of equilibrium for the analysis of statically indeterminate beams. So we make use of deflection equations so that we could analyze and we could somehow solve statically indeterminate beams. A number of analytical methods are available for determining the deflection of beams. The common basis is the differential equation that relates the deflection to the bending moment. The solution of this equation is complicated because the bending moment is usually discontinuous function, so that the equations must be integrated in a piecewise fashion. So there are various methods for deflection analysis, which is essential in terms of the different techniques for solving this differential equation. So in the analysis for the deflection of statically determinate beams, we have two methods that we are going to make use in this text. So we have the first one, the method of double integration. So this method is fairly straightforward in its application, but it often involves considerable algebraic manipulation. We also present a variation of the method that simplifies the algebra by use of discontinuity functions. The primary advantage of the double integration method is that it produces the equation for the deflection everywhere along the beam. That is the first method to use in the analysis of statically determinate beams. So the second method is a moment area method. So this moment area method is a semi-graphical procedure that utilizes the properties of the area under the bending moment diagram in the quickest way to compute the deflection at a specific location if the bending moment diagram has a simple shape. The method is not suited for deriving the deflection as a function of distance along the beam without using a computer program. So the first method is the double integration method. So basically here, if you're going to observe, we have here an illustration of our figure for the double integration method, and we try to have figure A and figure B. So this figure A illustrates the bending formation of the beam. So if we try to recall in the real beam, the displacement and slope are very small if the stresses are below the elastic limit, so that the deformation shown in the figure is greatly exaggerated. So the deformed axis of the beam is what we call elastic curve. So for this figure, we have here our this one refers to the deformation of the beam. This is figure 6.1a, and this one, figure 6.1b, refers to the deformation of the differential element of the beam axis. So if you refer to this figure A, we have to take note that we have here a horizontal coordinate of an arbitrary point A on the axis of the beam. So it is being referred as our x. So we let our x be the horizontal coordinate of an arbitrary point A on the axis of the beam. That is measured, if you're going to observe, it is measured from the fixed origin point O. So point O towards point A, that is our x. So as the beam deforms, so if there will be a process of deformation, so as the beam deforms, its axis becomes curved and A is displaced to the position A prime. So basically, if the beam deforms, so the axis becomes curved. So you have to take note. So this axis is the axis of the beam. So due to the deflection of the beam, its axis becomes curved. So you have now the curved axis. And our point A was displaced to the position of A prime. So, and the vertical deflection at point A is being denoted as V. So we have here our vertical deflection denoted by V, and this is being considered as positive, that is directed in the positive direction of the y-axis. So meaning to say this is upward. So since our axis of the beam lies on the neutral surface, so its length does not change. So therefore, the distance OA prime is measured along the elastic curve is also x. So there is no change on the length of the beam. So our point OA is equal to point OA prime, which is measured as denoted by x. So it follows that the horizontal deflection of A is negligible provided the slope of the elastic curve remains small. So this is our figure B. So do we consider the next deformation of infinitesimal segment AB of the beam axis. So we have here our elastic curve A prime, B prime of the segment which has the same length dx as the undeformed segment. So if we let V be the deflection at A, so we let our V, so this is our V, which is the deflection of A, then the deflection of B will be equivalent to V plus dV. So meaning to say from this point, this deflection towards point A prime is V. So the deflection at B prime would be V plus dV. With dV being infinitesimal change in the deflection over the length dx. So similarly, the slope angle at the ends of the deformed segment are denoted by, so this is the slope angle at the end of the deformed segment denoted by theta plus d theta. So this is our slope. So this slope here is denoted by theta, and this slope is denoted by theta plus d theta. And from the geometry of the figure, we can obtain that dv over dx is equal to sine theta, or approximately that is equal to theta. And the approximation is justified because theta is small, so we can have this equation. Dx is equal to rho times d theta. And our rho is the radius of curvature of the deformed segment, and that can be rewritten as 1 over rho, which is equal to d theta over dx. And substituting theta from the our equation, in the previous equation, we can obtain that 1 over rho is equal to d squared v all over dx squared. And when deriving the flexure formula in the section described, we obtained the moment curvature relationship. So this is our moment curvature relationship, that 1 over rho is equal to m all over ei. So we have to take note that our m is the bending moment acting on the segment. Our e is our modulus of elasticity. Our I is the moment of inertia of the cross-sectional area about the neutral axis. So substituting, we have here now our equation, d squared v all over dx squared is equal to m all over ei. And that is our differential equation of the elastic curve. And our ei called the flexural rigidity of the beam, which is constant along the beam. So we can have this equation, ei v prime is equal to m. And we have here our dv all over dx, that is our v prime, and this d squared v all over dx squared is our v double prime. And for the double integration of the differential equation, we can have this equation ei v prime is equal to the integral of m dx all over c sub 1, and for the second integration, it gives us ei v is equal to the double integral of m dx plus c sub 1x plus c sub 2. And c sub 1 and c sub 2, those are constant of integration that is to be determined from the pre-described constraints